Hello everyone. Today I will present our paper titled Towards an ASR Approach Using Acoustic and Language Models for Speech Enhancement. The authors are Khandokar Md Nayem and Donald S. Williamson from Department of Computer Science, Indiana University. I, Khandokar Md Nayem, will present this paper in ICASSP 2021. Let's begin. As introduction, monaural speech enhancement is a challenging problem that aims to remove unwanted noise from a target speech signal. For example, we are in a restaurant where many people are talking, music is playing too. It is often hard to understand what my friend is talking who is sitting just in front of me. A monaural speech enhancement system captures all these sounds using only a single microphone. The captured sound is called noisy speech. Then, the speech enhancement system outputs the clean target speech by removing unwanted noises. Now, increasing usage of electronic devices such as smart speakers, voice control devices, and hearing aids increases the need for improved speech enhancement. Advancements in deep learning have led the field towards a solution, but poor performance and unwanted distortions in noisy conditions require further improvements. Now we talk about some notable speech enhancement approaches. Speech enhancement is divided into two forms, either mask-based or signal-based approximation. Among mask-based speech enhancement approaches, in 2008, Lee et al. Proposed ideal binary mask. In 2013, Nayem et al. Proposed ideal ratio mask. In 2015, Aragon et al. Proposed a phase-sensitive mask. And Williamson et al. Present a complex ideal ratio mask. In 2019, Lee et al. Proposed a parametric complex valued time frequency mask. Now, signal approximation based speech enhancement has investigated too. In 2018, Leo et al. Proposed TASNet, which is an end-to-end speech waveform enhancement system in the time domain. On the other hand, in 2019, Wang et al. Proposed a speech estimation system in the TF domain. Notably, in 2016, Hershey et al. Suggest a binary mask estimation system for source separation tasks applying deep clustering algorithm. Now, whether it is real-valued mask estimation or speech signal approximation, speech enhancement task is a regression problem. Few works convert this problem as a classification task. In papers of 2012 and 13, Wang et al. Performed ideal binary mask estimation with support vector machine. In 2019, Rux et al. Proposed discrete codebook that estimate better enhanced phases and pose the problem as a classification one. Next, we see the usage of automatic speech recognizer in the task of speech enhancement. In 2015, Aragon et al. And Untitled et al. Separately utilized the ASR feature as input in speech enhancement. As our motivation, in paper of 2018, Haley proposed ideal quantized mask IQM. They use quantized values as individual mask values and they experiment with 4 different quantized values. Quantized ideal mask, however, does not consider spectral correlation along frequency axis. On the other hand, the language model is effective in ASR. In 2015, Graves et al. Show the advantages of incorporating language models in end-to-end automatic speech recognition tasks. Hence, language model can be a better way to incorporate the linguistic property of speech in an end-to-end speech approximation system. Now, traditionally phonetic or textual language models heavily depend on rich and robust datasets, which is now commercially in practice, whereas a spectral language model focuses on the spectral property of a human speech can be an alternate view. Therefore, we propose our approach, a signal approximation approach to approximate quantized time frequency spectral values where we subsequently apply a spectral model to generate more realistic speech. Quantization refers to treating time frequency speech estimation as a classification problem, where each time frequency spectral value is assigned to one of many quantized classes. The spectral language style model learns the transition probability of the quantized class across time and frequency to ensure more realistic speech spectrum. Our quantized spectrum estimation is analogous to acoustic modeling, and our spectral model is akin to a language model. So, problem formulation. In time domain, noisy speech is a sum of clean speech and noise. In the time frequency domain, Noisy speech is the multiplication of magnitude and exponent of phase. We can consider the noisy phase as a union of two sound sources, STK, which is the clean speech, and NTK, which is the noise. Therefore, we want to approximate magnitude of clean speech by learning the function Fi on noisy speech. In other words, we enhance magnitude of noisy mixture and use phase of noisy mixture to generate enhanced speech. Now we talk about speech quantization. Speech magnitude STK is unbounded and continuous valued. We constrain and quantize the speech by applying a scaling vector, a scaling function C, and quantization function Q chi. As you can see on the top left image, a time frame of clean speech spectrogram is real valued. On the right, the corresponding frame is quantized. Therefore, the actual TF values are changed into nearest quantized levels. A scaling function C limits the range of magnitude spectrogram between 0 and R. Chi is the quantization step size, which yields total D number of beans. Finding the appropriate quantized step is a crucial part of speech quantization. Therefore, we conduct an IRB-approved listening study using Amazon mechanical Turk to determine the best quantization level as assessed by normal hearing listeners. We consider 5 different quantization levels using a step size of 2, 1, 0.25, 0.0625, 0.015625, which are separately compared to clean reference signal. These quantization levels result in quantized speech with equivalent signal to quantized noise ratio SQNR of 14.21 dB, 17.78 dB, 26.5 dB, 36.25 dB, and 46.93 dB respectively. The study session contains a total of 30 questions, which is preceded by a practice sessions of 7 questions. 10 participants who are native English speakers over the age of 18 participated. On the right-hand side, we show the actual question from the listening study. In each question, a participant will listen to 2 audio signals. Then they provide a preference score using a Likert scale ranging from -3 to +3. From the collected responses, we analyze to determine the appropriate quantized step. The right figure shows preference score for different quantization steps, quantized level on x-axis and preference scores from participants on the y-axis. For quantized level, 2, 1, and 0.25 negative scores indicate that these produce noticeably poorer sound quality. For quantized step 0.0625, the preference score is very close to 0, which means it is quite compatible with clean signal. Additionally, previous studies show that speech with SNRs greater or equal to 20 dB achieves significantly good perceptual quality and intelligibility. This is also the case in our study when chi is 0.625. So we choose 0.625 for quantization, which results in 1,600 quantization classes. So we design our speech enhancement model. We adapt a Chimera++ type model structure for estimating the quantized speech value at each TF point. On the right hand, we show our proposed model network for speech enhancement. Multiple bidirectional LSTM layers are applied to learn a TF embedding for the inputted speech. In the output layer, we use a Y-shaped structure with 2 branches. The rightmost branch predicts the quantized class probability for the TF time frame using a linear and softmax layer. This branch of the network has 2 losses, a cross entropy loss to assess classification performance and regression loss, where the estimated expected quantized value is computed at each TF bin and compared to the true quantized value using the mean score error. The left branch of our model performs deep clustering to separate speech from noise. It serves as a regularizing term for this approach. We form the embedding vector matrix V and source level indicator matrix Y. The source level matrix V is learned by minimizing the following objective function for the deep clustering loss LDC. The overall loss function of our network is defined by L with hyperparameter lambda1 and lambda2. Now we apply quantized spectral model to ensure more realistic speech enhancement. Traditional language model is applied at the word or phoneme level, where the effectiveness of the language model depends on the text and its vocabulary. Here, we propose an alternative view of a language model, where we consider each quantization level as a word. We consider the bigram language model, which we refer to as quantized spectral model. We consider per frequency QSM, where the probability of compute are computed per frequency channel, and each entry refers to the transitional probability between two time consecutive quantized levels. On the top right figure, we show that a FQSM is defined for each frequency channel. Therefore, we have in total F numbers of FQSM. Mean QSM is defined across all frequency channels. Therefore, we have a single MQSM. Now we incorporate the quantized spectral model into our speech enhancement model. Therefore, this network predicts the quantization sequence condition on both class probability and transitional probability. QSM is trained separately and remain frozen when network weights are updated during backpropagation. The enhanced speech sequence SQ is of the optimal quantized class sequence, which is calculated by maximizing both class and transitional probability. Using a beam search algorithm, we can solve the equation and find the best quantized class D for each SPK-Q. Now, dataset. We train and evaluate using IEEE mail and timid speech corpora. We propose QSM. QSM is trained on the clean speech of both these datasets. 4 noise types are used. They are speech shape noise, cafeteria, factory, and level. We train and evaluate our networks in 3 SNR levels, -3, 0, 3 dB. We also test the models with 2 additional SNR, -6 and 6 dB. We compare few different approaches to test the performance of our proposed approach. We compare our model against the Chimera and Chimera++, which are mask-based approaches. Chimera predicts a magnitude mask, while Chimera++ estimates a phase-sensitive mask. We use the Chimera++ model to estimate the ideal quantized mask. We denote them at Chi++ IQMX, where X refers to the level of quantization. Additionally, we compare with a Chimera++ network that predicts quantized speech, Chi++ quant, which is proposed without QSM. Our proposed approach, we use the same Chimera++ network and investigate with different QSM techniques. We incorporate MQSM and FQSM. We also experiment with optimal quantization class sequence decoding algorithm. We try a greedy approach and n-beam search approach. Now, experiment setup. The baseline network has 4 LSTM layers with 600 units. Dropout layers between each LSBS stem layer with rate 0.3. Softmax and sigmoid activation function are used for the output layers that predicts quantized class and embedding approximation respectively. For the embedding vectors, we use vector dimension epsilon 20 and source dimension Z2. We use atom optimizer with learning rate 0.001 and do early stopping by evaluation set. We use loss functions parameter lambda 1.5 and lambda 2.975. Here we show the results of our experiment. In the table, we show average scores for each approach. Comparison metrics are best, scale invariant SDR, and extended S2I. We compare for both single speaker and multi-speaker cases. Mixture in the original noisy speech, which are unquantized. Our proposed Chi QSM outperforms all the other models with per frequency QS information, and Chi MQSM closely follows. Additionally, Chi++ quant exceeds the Chimera model in all performance metrics, but it still has lower scores than QSM infused models, which indicates the advantages of a spectral model. For optimal quantized class decoding, we use both greedy and n-beam search approaches. Beam search shows superiority likely because it covers bigger subspace with 100 class candidates. In conclusion, we propose quantized speech classification approach with an ASR language model, successfully enhances the speech mixture and outperforms TF masking-based approaches. It shows that signal approximation can be done successfully if appropriate training target is considered. This approach, however, considers only bidirectional spectral models, which are generated by considering only along time transitions. In future, we will explore high-order n-gram models that consider both temporal and spectral transitions to enhance both magnitude and phase responses. Thank you all.